In this video, we're going to learn about implicit differentiation. So we've learned how to take derivatives of a function, and we find dx dy, so we find the derivative of x, we define the derivative of y, we work with those. So we use implicit differentiation when we can't first solve the equation for y in terms of x. We can't get it by itself, or doing so is just too tedious. So we're going to need to remember that our notation. So if I had y equals 3x, when I find the derivative, I can write it as y prime, or I can write it as dy dx, the derivative of y with respect to x. That's why it's in the denominator. So if I want to find the derivative of x squared plus y plus 3 equals 0, I could solve for y and then take my derivative. So this equation has an implicit meaning. This is an explicit formula with an implicit meaning that is implied or understood that it's describing y as a function of x. So this is an implicit function because we don't have one variable all by itself. I can make it explicit if I solve it for y. So that's the difference between an implicit and an explicit equation. So the problem is sometimes I can't easily solve for y. I can't figure out what dy dx is. And that's when we use implicit differentiation. So just to review, we can find the derivative for the explicit equation, y equals negative x squared minus 3, because I find the derivative of y with respect to x, that's dy dx. And I can just use my rules over here, so this would just be negative 2x. So I'm finding dy dx. Okay, nothing crazy there. But now here, I give you a harder equation. I have 2x to the third minus 5y squared equals 5. And I want to implicitly differentiate this because I can't really solve for that y by itself. So what I do is I take the derivative of each piece. So I use my rules. Derivative of 2x to the third is 6x squared. The derivative of 5y squared, I'm still using my power rule, so that's where I get negative 10y. But I don't know what the actual derivative of y is, so that's where that dy dx is. Okay, so I'm actually using my chain rule. I took the derivative of 5y squared times the derivative of whatever just the function y is. So we got to remember to do that. And then it equals, I can't forget the other side, don't forget to differentiate the right side. The derivative of 5 is just 0. And so then to actually get my derivative, I need to solve for that dy dx. So I added my 10y dy dx to both sides. And I didn't show that here, so I'll show you those steps just in case. So that equals my 10y dy dx. And to get dy dx by itself, that's where I divided both sides by 10y to get my dy dx. And then I can simplify. So I have 3x squared over 5y is my derivative. And remember, we can use derivatives to find slopes at certain points. We can find the equation of a tangent line at a certain point. So we're going to keep going with this example and actually use this implicit derivative. Okay, so we had our implicit derivative we found was negative 3x squared over 5y. But now I want to find the equation of the line tangent to that curve at the point 2, negative 1. So that means I need to know the slope at that point. Well, that's what dy dx is. It's telling me the slope, but I had to plug in my x value and my y value. So I end up with a slope of negative 12/5. And then I'm just writing the equation of a line. This time I use the point slope form, y minus y naught equals m times x minus x naught. So y naught is my initial starting value, negative 1 for the y. I have 2 for my x, and I plugged in my slope. I clean it up, and I can get my equation. So y equals negative 12/5 x plus 19/5. All right, let's try one more. This one's a little bit tougher, lots of algebra involved. So I have 5 equals 3x plus 2y over cosine y squared. So I'm going to start by saying, well, I don't want to use the quotient rule if I can help it. So I'm going to multiply both sides by cosine y squared. So I have 5 cosine y squared equals 3x plus 2y. All right, by multiplying by both sides, I got it out of the denominator. And now I'm going to take the derivative of each side. So the derivative of 5 cosine y squared is going to be 5 times negative sine y squared times 2y dy dx. So it's using that chain rule there. So that's the left side. Equals on the right side, the derivative of 3x is 3. The derivative of 2y is plus 2 dy dx. Okay, well I want the dy dx's all together on one side. On the left side, I can clean this up. 5 times negative sine y squared times 2y dy dx is really negative 10y sine y squared dy dx. And then this positive 2 dy dx on the right side I want to bring over, so I'm going to say minus 2 dy dx over on the left side, and that still equals 3 on the right side. And I'm trying to solve for dy dx, so notice it's in both terms on the left, so I can factor out dy dx, and I'm left with negative 10y minus 2. Oops, sorry, I forgot my sign. Ooh, careful there. I forgot my sine y squared. Phew. And now to get dy dx, I'm going to solve by dividing. So I have 3 over negative 10y sine y squared minus 2. So it's a scary looking derivative. Lots of pieces going on. I could have done this by using quotient rule, but it would get a lot messier. So this is what we mean by implicit differentiation. We're taking the derivative of the whole equation, every piece, and then solving to get that dy dx by itself.